I can give you any orbital and ask you to draw it. So for example, let's say I said, I want you to draw a 1s orbital. You need to be able to draw any s, any p, or any d orbitals. So for an s orbital, it's what shape? Sphere. That's it, you're done. How many nodes would this have? It would have, yeah, it's n minus 1 is the equation. If you don't know this equation, you got to memorize it. Okay, so n is 1, so there's 0 nodes. So we're done. So you always want to label nodes. If I asked you to draw 2s, you would draw a sphere, but it would be slightly bigger. So if you were comparing to, if you were just drawing the 2s, you have no basis of comparison, you just draw a circle. But if there was another orbital there, another s orbital that was a 1s, you would draw the 2s larger than that. Okay, how many nodes does this one have? Yeah, this one, 2 minus 1, so this has 1 node, and you draw a concentric circle inside the sphere, or inside the circle. If you had to draw a 3s, same thing, you draw a circle, but it would be slightly bigger. How many nodes does this one have? This has 2 nodes. 3 minus 1 is 2. So you're going to draw 2 dashed circles inside the circle. Should I draw 4s, or do you get the idea? You got it. Okay. Now, for the p's. Let's draw the 2 p's first. For any given s orbital, for a given n, so for example, 1s, how many 1s orbitals are there? Just 1. Okay, so there's 1 2s orbital, and there's 1 3s orbital, etc. Why? Does anybody remember why that's true? What quantum number tells you the number of orbitals? Not L, m sub L, yeah. So in this case, let's still stick up here for a second. What's L up here? In all these cases, it's s, which is 0. That means m sub L equals also 0. It goes from plus L to minus L. So plus 0 to minus 0, that's just 0. So there's one m sub L value. That means there's only one s wave function. That's it. For a p, however, again, what's n? 2, and L is? Yeah, it's the letter p, which is the number 1. That means m sub L is? Yeah, 0 or plus or minus 1. Meaning if if L is 1, then m sub L goes from minus 1 all the way up to plus 1, or minus L up to plus L. So minus 1, 0, plus 1. There's 3 values of m sub L. That means there's how many orbitals? 3. Okay, so the number of orbitals always matches the number of values of m sub L. So there's 3p orbitals. There's the 2px, which is this thing, whatever you want to call it, 2-leaf clover or dumbbell or whatever. On the x-axis, there's a 2py, which is the same thing, but it's on the y-axis. And just for convenience, I put the axis wherever is convenient. Okay. And there's the 2pz, and just out of convenience, make that the z-axis. Okay. So that there's 3 orbitals. Every p orbital has 3. So 2p orbital has 3, a 3p orbital has 3, a 4p has 3 of them. They're the x, y, z direction. You need to be able to draw those. Okay, the 2p orbitals have how many nodes? Yeah, you take n and subtract 1. 2 minus 1, there's 1. And this node is visible from the outside. It's here, here, and here. Here, I don't know why, I just drew it as a line instead of a dash, whatever. Okay? So there's one node, it's going through the middle of it. A node, just so you know, a node represents where an electron does not exist. So a node is where there is no electron. The shape you see is where you're most likely to find an electron. So the orbital, this lobe here that looks a little bit like an 8, that's where you're going to find electrons. Okay, most likely, the highest probability finds electrons. That means, say, for the 2s orbital right here, you're going to find, for a 2s orbital, electrons in that spherical shape. except in the spherical shape that is inside there, the dashed line. Okay? So it'll be anywhere in there, most likely, or the highest probability of being in here. Could be somewhere else, but most likely it'll be in here, but not on the dashed line. Same for these, it'll be here, but not on the nodal line. What is the name of this kind of node right there? It's called an angular node. When it has a linear shape, it's called an angular node. What are the names of these kinds of nodes up here? These are called radial. Radial nodes look spherical. So there's radial nodes that look spherical. There's angular nodes that look linear. Those are the two types of nodes. You need to be able to label the different types. So let's do a slightly harder one. A 3P, and somebody pick a letter, X, Y, or Z. Okay, I heard Z first. So to draw 3PZ, what you'd want to do is draw one of these. And what axis is this? Z. You just look here. It's Z. It's given by that. Now what's N? 3. So number of nodes is? It's, 3 minus 1, which is 2. So let's label those nodes. A p orbital is born always with one node, right here. So this is 1. Again, the name of this is? Oh, I already wrote the A. Oh well. Angular. Okay, there's one more node. It is called radial, and it is just circumscribe a circle in here. So you're not drawing the other part of the circle, just the part of the circle in the p orbital. And this is called a radial node. And there's your two nodes. Okay, so that would be the correct drawing for a 3PZ. If it was a PY, you just change the axis to Y. If it was a 3PX, you change the axis to X. Do you need me to do a 4P orbital? No? Okay, let's move on to Ds. Ds now. A D orbital, what's L equal to? Yeah, L for D means 2. That means what's the smallest value for N? 3. It can't be 2 because it can't be equal. So 3D is the smallest, what we would call the lowest energy D orbital. Because it has the smallest N value, the lowest energy D orbital. What's M sub L? Plus or minus 0, plus or minus 1, plus or minus 2. Are there more? That's it. So there's 5 values. Why? Because L determines M sub L. If L goes from minus L to plus L, or M sub L will go to minus L to plus L. So minus 2, minus 1, 0, plus 1, plus 2. So there's 5 values. So what are we expecting? 5 D orbitals. 5 different D orbitals. Here they are. Let's do them for the 3D, the lowest energy. There's the 3D XY. That's on the X, so these give you the axis. It's on the XY axis. And it's a clover leaf that goes between this axis. There's the 3D, we'll do the nodes after we draw everything. 3D YZ, again, Y and Z tell you the axis. It looks identical to the previous one, except there's different axes, a Y and a Z, instead of X and a Y in the previous. Looks like that, and then there's the 3D XZ. Again, identical to those two, except it's the XZ axis. Otherwise, it'll look totally identical. There's 2 more. They look a little different than the previous 3. There's the 3D X squared minus Y squared, and yeah, you should know these names. 3D X squared minus Y squared, these again tell you the axis. It's on the XY axis. However, as opposed to the previous 3, as opposed to the 3D XY, this is on the axis, not in between the axis. So it's identical, it's just shifted 45 degrees from the one above it. That's the only difference. And then the final one is different than all the rest. It's the 3D Z squared. So you just look at the Z and it tells you it's on the Z axis. It kind of looks like a p orbital, but it has a ring around it, or it kind of looks like a hoop. It's doing the hula hoop. Okay? So it's on the Z axis. It's called the 3D Z squared. So notice the squareds mnemonically could help you remember it's on the axis. If it doesn't have a square next to the variable, then you can try to remember it's off-axis. These are the 3D orbitals. Okay, we didn't determine how many nodes there were. How many nodes? Yes, n minus 1 or 3 minus 1, 2. And so every d orbital is born with 2 nodes. And on these 3 here, the nodes are just the axes. So the nodes are the axes on these. Kind of hard to see, but I'm doing it in black ink. And here, the nodes are between the axes for the 3D x squared minus y squared. So the dashed lines show the nodes. On the top ones, it's the axis. On the 3D x squared minus y squared, it's between the axis. What are the names of this type of node? They're all angular. It's born with 2 angular nodes. Don't worry about drawing the nodes for the 3D z squared. It looks somewhat conical, which I can't imagine you possibly drawing and a TA understanding what you're drawing. You can look on Google if you're curious, but I wouldn't ask you to draw the nodes of this one, just because I can't trust that you would draw it well. Ditto for me, I wouldn't be able to draw it either. Okay, so let's try something that's not that. Let's do a 4D, and somebody pick some letters for me to do here. X squared minus y squared. Okay? So, let's go through all this. What's n? 4 is the first number. What's L? Yeah, the letter D goes with the number 2. What else do we want to know? Nodes. How many nodes? Yeah, 4 minus 1 or 3. Now we can draw it. X squared, so the squares tell me it's on axis, so let me draw the axes first. X and y, I know it's x and y because of the subscripts. And since it's squared, I know this is the one that's on axis. So I'm going to draw the one that's on axis here. There it is. Okay? And the d orbital is born with 2 nodes. They're the ones that bisect it in half on both planes. So these are actually planar nodes. And I can label these, this one and this one are called angular nodes. So there's 2 of the 3. It's born with 2 of the 3 always. Just like a p orbital is born with 1 node that's also angular. Where is the final node? Yeah, it's a circumscribed circle. I'll draw it. I'll zoom in a little bit. Hopefully it's somewhat visible here. It's a circumscribed circle. Just try to draw a circle as best you can inside the node. And this is called a radial node. There's the third and final node. Yeah, there's a question? Yeah.
Does it matter if the x is on top and the y is on the right?
Oh, does it matter if you flip the x and the y as far as drawing the axis? No, it doesn't matter. You can even draw them however the heck you want to, as long as it's oriented correctly. But you might want to think, will a TA understand my drawing? Because they're grading, one TA is grading 400 of just one question. So one TA is looking at this, and if you don't make sense, but the other 399 do, that's going to be a problem. Okay? So make it as understandable as possible. Okay. Can I move on? Is that enough? Oh, yes.
Is the radial node, is the z-axis is not listed? And
the z, so the question is, where's the z-axis is right here, but it's not, it's in and out of the plane. It's this way, it's coming towards you, but it's not relevant to the drawing, so we don't include it.
So is that an outline of the sphere, or is it just a circle?
Is that outline? It's actually spherical. Yes, because it's the distance from the center out to the edge in every direction inside the cloverleaf. Yeah, you can't draw better than, you'll see in class, I will show you an artistic rendering, I think of a 5D x squared minus y squared, that I wouldn't be able to draw, but you can just see what it really looks like. There's also phases that I'm not going to really get into, but are going to be important in chapter 10. So I'm kind of avoiding the phases as well. You'll see them more in chapter 10 again. because they're more relevant there.